All right, let's talk about conservation of energy. I've got an object here, a rock or something. It's got a mass of 2 kilograms. It's 4 meters off the ground. And I ask here, when the object is dropped, how fast is it going just before it hits the ground? So I know that the distance it's going to fall is 4 meters. I know its acceleration is 9.8 meters per second squared. Its initial velocity was 0, and I'm interested in what its final velocity was. I should use Vf squared equals Vi squared plus 2AD. This guy is 0, so I'm going to get Vf is the square root of 2GD, which is going to be the square root of 78.4. If you plug in, you can trust me on that, at 8.85 meters per second. So at that point, how much kinetic energy does it have just before it hits the ground? Well, I pull up my handy EK formula, which is 1/2 mv squared. I'm going to get 1/2 times mass of 2 times this 8.85 squared, and I punch it in my calculator and I get 78.4 joules. And I'm getting to a point here, just doing some math so I can look at some numbers. How much Eg did it have at the top? Well, I get out my handy Eg formula, which is mgh. It had a mass of 2, 9.8, 4. I get 78.4 joules. So the question here is, what do I notice? It had, just before it hit the ground, it had 78.4 joules. Before it was dropped, it had 78.4 joules of energy. What do I notice? EK equals EG. Yes. So we can conclude then that therefore when energy changes from one form to another, say no energy is lost. I don't actually like that definition very much, this no energy is lost, because sometimes energy is lost as heat, and I don't want you to get confused about it. So I would like to put a little box around this here, and then over here I'm going to put one form to another. When energy changes from one form to another, all energy can be accounted for. Yes? None of it's being lost. I'm like, where the hell did that go? I got to be able to figure out where it is. None of it's being created. It's not appearing out of thin air. I can account for all of it when it's changing from one form to another. So let's look at this roller coaster car. Here it is at the top of a hill. It has, let's just say randomly, it's got 1,000 joules of kinetic energy. It's got 1,000 joules of potential energy. How much mechanical energy or total energy will it have? 2,000 joules. Okay. What does that mean? What will its total energy be right here? Answer, 2,000. How about here? Answer, 2,000. Here, 2,000 here, 2,000 here, 2,000 here, 2,000 here, 2,000 here. It's going to be 2,000 joules throughout this entire trip as long as there is no friction. As long as there's no friction, total energy should be the same throughout this entire trip. Okay, what's happening to it? The breakdown is happening to it. Right here, it's half and half. But as it starts to fall and get closer to the ground, this answer, this 1,000 is going to go down, and it's going to start getting faster, so this is going to go up. And the changes will be equal. Yes? And then it's going to max out at EK down here, and then it's going to start going up again, so it's going to slow down. And EG will start to get bigger, and EK will be smaller. But the whole time, E total will be 2,000. Don't think that it won't be. Okay? So if we look at a sample question here, I've got a ball of mass 3 kilograms is dropped from a height of 14 meters. How fast is it going when it is 8 meters from the ground? This is an energy question. And I'm going to suggest that you do your given like this, that you do a given for 14 meters and you do a given for 8 meters. When it's 14 meters up, its mass is 3 kilograms. Its height is 14 meters. G is still 9.8 meters per second squared. And its velocity is 0. Here, its mass is still going to be 3 kilograms. The height over here is going to be 8 meters. G is still going to be 9.8 meters per second squared. Here, that's what I want to find. I want to find out the velocity. Now, I know that the energy it has here must be equal to the energy it has at 8. So I'm going to write here that the energy at 14 meters has to be equal to the energy at 8 meters. I know this to be true. What type of energy could it have at 14 meters? It could have some potential, and it does, and it also could have some kinetic. What type of energy could it have here? It could have, again, some potential, and it could have some kinetic. But it turns out, since the velocity at 14 meters is 0, it will not have any kinetic energy, because V is 0, and it's in the formula. If there's a V in the formula, it's going to turn that to 0. So let's write up the formulas for each. That would mean this is mgh, I'm going to put 14, equals mgh8 plus 1/2 mv squared. What do I notice about all 3 terms in this equation? They all have what in them? Correct, an m. So I'm going to cancel out the m's. Doesn't matter. Mass is not a factor in how fast something will be falling. So I'm going to get 9.8 times 14 equals 9.8 times 8 plus 1/2 v squared. And I'm going to get, I work this down, and I'm going to get v is 10.8 meters per second. So what I did here is really important. These 2 lines here are very important, and I would suggest them to be a basis for all your answers. I know that energy is always going to be conserved, so the energy at any point will be equal to the energy at any other point, and you just have to pick your point of interest in your question. For me, it's at 14 meters and 8 meters. It could have been at 14 meters and 0 meters if I was talking about the top and the bottom. And then the next line, I usually write them all out. Even if I know in my head there's not going to be an EK, I'll still write it out in the next line and then cross it out so I'm better explaining my answers. So people who look at my answers can say, oh yeah, okay, I understand what he was doing there. Not just somebody looking at my answer and thinking, well, why didn't he write an EK there? I always put them down and then I get rid of them after. And then you work your way down using some math. And that is all about conservation of energy.